Yeah. So this is a question on Dijkstra's path, shortest single source shortest path algorithm. Okay. So basically in this question they'll give you a start vertex. Okay. So in this question this S node was the start vertex. So now starting from this node you'll have to find the shortest path that connects all the nodes to this node. Okay. So now in order to begin, first we need to make two tables. Okay. A D table and a pi table for all these vertices. I'll just make that and be right back. Hey, you're back. Okay, so like actually use a scale and stuff to do this, okay? But for now it's fine only, no scale. Hehe. Yeah. So now the initial values, okay? Whichever the start vertex will always have a distance of 0, okay? And rest all will have distances infinity. This is basically to state that since you're at the start vertex, if you want to go to the start vertex only, it will take you no distance at all, right? But however, if you need to traverse to any other node, right now the distance is unknown. So we denote that unknown using an infinity, like an upper bound. It can't be more than infinity, no? Max to max infinite distance only. Vese. And for the rest of these, this is your pi table, okay? This will keep track of the previous node, okay? As in the next step you'll see exactly how it keeps track of the previous node. For now just know that you need to make two tables after each step. Okay, we need to perform around, let's say how many vertices are there, 1 2 3 4 5 6. Since there are 6 vertices, we'll have to draw these tables 6 times in total. Okay, and then finally we'll get a resultant single source shortest path wala graph. Okay, so now let me draw the table again and be right back. Okay, so now this will be our next step. Okay, so now firstly we need to check for the vertex which has the smallest possible distance value. Over here we can see that our vertex S has a distance of 0. Okay, because this is a start vertex, we'll be starting from here only, so it's kind of obvious. But basically in each iteration or each step we find the vertex with the smallest distance and start from there. So now let's look at a graph. Okay, if you look at our vertex S, from S what are the adjacent nodes? The adjacent nodes are A and B, right? You can go from S to A or S to B. Let's consider node A first. Okay, so now if you go from S to A, what is the distance that you need to traverse? It would be distance of S itself, that is 0 plus 1. Okay, so 0 plus 1 is 1, correct? So distance to travel from S to A is 1. Now let us check the table to see what value of distance for A is there. Okay, so now if you look at it, A has a distance of infinity and we are concerned with minimizing the distance. Since 1 means 0 plus 1, actually 0 plus 1 is less than infinity, that is 1 is less than infinity. Therefore we can update the value for the distance of A. Okay, so now if you want to traverse from S to A, you'll take a distance of 1, and this though is our start vertex, it will be 0 only. Now let us have a look at B. Okay, if you want to traverse from S to B, what is the distance, total distance that you need to travel? The total distance you need to travel is the distance taken to reach the start vertex, which is 0, plus the distance of the edge or the weight of the edge. So the weight of the edge is 5, no? So 0 plus 5, 5. Now we check in the distance table whether phi is less than the current distance value. Okay, now the current distance value is infinity and phi is obviously less than infinity, so we shall update that here too. Okay, good. And these will be infinity, infinity, infinity. Now we can also have a look at the pi table. Okay, since this is the start vertex, this one will always be null. Now we went to A and B. Okay, we went to vertex A, vertex B. But we started from which node? S, no? Like the previous node of A is S and the previous node of B is also S. So we can just mention that here and these will be null because they haven't been updated yet. So this was our second iteration. I'll just draw the tables and be back again. Here, back. Okay, so now as you saw, we selected node S, no, in the previous one. So we can just cross that out. This is like rough work, that is just to keep track. Okay, like I have already processed this vertex, now I'm no longer concerned with this vertex. Vese. Now this is only for the selection process. Okay, so now we need to select as in the first step. Okay, we selected the vertex with the smallest distance, no, that is 0. But now since we process this one, we hide it and now we check the remaining vertices, sorry, and we see which vertex has the smallest possible distance value. As you can see, vertex A has the smallest possible distance value of 1. So the next vertex that we will move to is A. Okay, so now we'll be concerned with the adjacent neighbors of A itself. And we can write down this and this as it is. These two values won't change, 0, because this is the start vertex and we just reached A, no? So A to A will remain the same only. Now from A, what are the adjacent vertices? Those are vertex C, vertex D and vertex B, because you can go from A to C, A to D and A to B, but you cannot go A to S because this is a directed graph. Okay, directed weighted graph uske liye. So you can only go from A to B, D or C. This is a C, okay, not an E. This is E. Yeah. So first let's look at C, okay. Now let's say you want to go to node C, okay. What is the distance to go to node C? The distance to reach node C would be the distance to reach node A plus the distance of this edge or weight of this edge. The distance to reach node A can be gained from the table, okay. So we need to travel a distance of 1 to reach node A plus another 2 to reach C. So you do 1 plus 2 is equal to 3. Okay, so the total distance to reach C is 3. Now we check, is 3 less than equal to infinity? Yes. So we can update the value of C, the distance of C in the distance table, and if you want you can at the same time update that the previous node of C is A. So you can just show that in this table over here. Also, as this is the start vertex, it will always be null, the previous node for that. Okay. Now we finish looking at C. Now let's look at D, okay. Now the distance to reach node A, as you can see, is 1. Now once we reach 1, we need to go till D, no? So if we travel from A to D, we get another 1. So distance to reach A is 1 plus to reach D is 1. So 1 plus 1, 2. So the distance to reach D is 2. Now we check in the table, distance table, whether 2 is less than equal to infinity. Since 2 is less than equal to infinity, which is true, we can update the value over here, okay. We can write 2 over here. Nice, sir. And we can also update this as the previous node. Now finally, we reach node B, okay. These two have been checked. Now, if you go from, the distance to reach node A is 1 plus the distance to reach node B or vertex B is 2. So 1 plus 2 gives us 3. Now we check in this distance table. Here as you can see, the entry is not infinity because we just calculated that from our previous result. No? So now we check, is 3, 1 plus 2, 3, no? Yeah. Is 3 less than 5? Yes, it is. So we shall update this entry and update the previous node of B as A. Okay. And now all the remaining stuff will, all the other vertices will remain the same as it is because we have finished processing all the adjacent nodes of A. So E was not defined and this one was S. Nice. Okay. So now we finished processing this and this. Now next we'll be only looking at this remaining table. Oh, I forgot the infinity. We'll be only looking at this remaining table. Okay. I'll be back after doing this again. 1 second. Hey, back. So as you know, we finished processing node S and A. Okay. And also the starting vertex will always be 0 and it will always have a null value. So you can fill that in directly. Now, since we finished processing this, these marks are only for cross-checking, okay, like rough work. In the actual numerical, no need to do that. If you want to do it, then you can do it with pencil or something. So now we hide this, okay. So now among these are remaining vertices that are still left to be processed, okay. So now we check out of these remaining vertices, which vertex is has the smallest distance value. As you can see, vertex D has the smallest distance value of 2. Since this is the smallest value, we will be considering this as our next node, and you can write this as it is and uska entry as it is. Since you're considering that, okay, this will remain as it is, D. Now let's look at the graph. As you can see, the adjacent node of D is only E, okay. C, A, and B are not adjacent nodes of D because there's no outward arrow going towards them. Only arrows are incoming. So C is not adjacent because we can't travel to C from D. But however, you can travel to E, no? Like D say E, because the arrow points in that direction. Basically, in directed graph, wherever the arrow points, there you can go. वैसे. So from D, you can only go to node E. So that is the only thing you need to be concerned with here. Only one vertex you need to check. Okay. So now firstly you'll ask the question, what is the distance to D here? So the distance to D here is 2, as you can see. The distance to reach D is 2. Okay. And now if I want to go to E, so I'll add 2 plus this distance over here, this weight of this edge over here. So 2 plus 2 is 4. Now we shall check in our pi table whether 4 is less than E ka distance. We are going to E, no? So we'll check E ka distance. Is 4 less than infinity? That is E ka distance. Obviously, yes it is. So we'll update that. And the previous node for E would be D, no? Because we are just traversing from D to E. So the previous node also is D. And since that was the only vertex here that is connected to D directly, that is the only one we need to process. So the rest of the entries will remain the same. Nice, sir. And now we have processed this, we have processed this, and we have processed this. I'll draw the tables and be right back. Here, back. So this was a start vertex. So I just filled the entries with null and 0 here because that always remains the same. It won't change no matter what. Okay, so now we need to find the, for the next step, we need to choose a vertex, no? The vertex with the smallest possible distance. However, we need to keep in mind that this node, and this node, that is S, A, and D are already processed, no? So, we can hide this like that, okay? Just hide this one here. Yeah. Okay, so we hide this here. And now you can see that the only 3 vertices that are left are B, C, and E. Okay, so now which of these have the smallest possible distance? You can see that B and C both have the smallest possible distance, no, 3 and 3. So which one to choose? In order to avoid ambiguity between which one to choose from these two over here, we can just say that the one that comes first in the alphabet, B comes first, no, B, A, B, C. So B. So since B comes first in the alphabet, we'll choose that. Okay, so the next vertex that we choose is B. So we can write B ka values as it is, and now let's have a look at B. Okay, as you can see, from B we can only reach one vertex, that is D, and also the distance to B that we can get from this table, distance table, the distance to go to B is 3. Okay, so distance is 3. 3 plus 2 is 5. So according to this, it tells us that the minimum distance is 5, okay, according to B. Now let's check whether that is actually true or not. The minimum distance to go to D should be 5. But as you can see, 5 is not less than 2, no? So this value will not get updated. And since B only had one neighbor D, so that is all it will check. So in this case, our table completely remains the same. S, A, D. Nice. Also, after each step, okay, like we are considering one vertex, no? So we can say this thing. The vertex with minimum D value or distance value is S. So we extract S. In this one we used S, no? So uske liye S. Then similarly for each step we can write this statement, okay? The vertex with minimum D value is, in the second step we took A, no? Yeah, we took A. So the vertex with minimum D value is A. So we extract A. वैसे. Similarly for the next one, the vertex with minimum D value is, in this case it was D, no? So the minimum D value is D itself, D vertex. Therefore we extract D. Means we are processing one node at a time, no? So if you write these statements like that, then it will look nice and presentable and easy for the person to check also. वैसे कुछ. Okay, so yeah, keep that in mind. I don't write it just because I I'm solving in rough or something. No idea. Okay, I'll just draw the table and be back. Okay. Yeah. Okay. So I filled the table with the new values. Now, as you can see, I made the new table and just filled the start vertex value. Sorry. Okay. Now we know that see S is processed, A is processed, D is processed, S, A, D, and just recently we processed B, no, in the previous step. So we have processed S, A, B, D. Only two vertices left. So two more steps are left. Okay. So now we can just hide these vertices and then check. Out of these two vertices that are remaining, this is C. Okay, C. It kind of looks like A, but yeah, it's C. So between C and E, the two vertices remaining, which has a smaller distance value. As you can see, C has a smaller distance value. So that will be the one to go next. I'll just mark it here also, so that it becomes more convenient to understand. And since C is going next, uska distance value and previous node will remain same. Okay. Now let's have a look at C. If you look at C, we can go from C to E and C to D. That means node E and node D are the two adjacent neighbors of C. Now, the distance to C is 3, okay? So, if you want to go to E, we'll travel to C first. So, 3 plus the weight of this edge. So, 3 plus 1, 4. So, according to this, according to node C, it will take a distance of 4, okay? Now, whether that is minimum or not, we can check by looking at this table. As you can see, we already have established that the distance to reach E is 4, right? So since 4 is not less than 4, we shall not update this value. So this value will remain as it is. And you can write this value as well over here for the previous node. However, if there was a 5 over here, and since we got a 4 from this graph, and 4 is less than 5, then we would have updated over here. But since that is not the case over here, we did not update anything. Okay. Now we can also go from C to D, okay? As you recall, the distance to go to C was 3, and from if we go to D from C, it will be 3 plus 3, 6, okay? Now, is 6 less than the distance of D? Is 6 less than 2? Obviously not, no? So we will not update the value of D, even the value of D will remain the same. And now as you can see, C has no other adjacent neighbors, okay? So you can just, copy back the remaining values. They won't change at all. Yeah. Okay. And then finally, for the last one, now there's only one vertex remaining, no? This is the one with the minimum value, okay? So I'll just make the table and be back. So we'll be selecting that next. Yeah. Okay. So now we only have one vertex left to process now. So after this step, all our vertices will be processed. So for the last vertex, we extract it first. We can say, since we can write the statement that I wrote here, like after each step you can write that, like the vertex with the minimum value is E, so we extract it. So now after we select E, okay, as you can see, E has no further adjacent nodes, no, like from E you can't travel anywhere. If there was any outward arrow like that going out, then we could have, but since there is none, E will remain as it is. Okay, so now since we are done this thing, what do you say, with solving the numerical, now we can get onto the graphing part, no? So now means like you need to draw the final output or something, right? So in order to do that, we can just make use of a graph, okay? So first look at the vertices of the graph. As you can see, they are placed as in this way, S, A, B, C, D, E. So draw the vertices in the same way, okay? S, A, B, C, D, E. Now, if you look at the phi table, okay, that you got at the end, this is the same one. I just copied it here for convenience, okay? So then this will give you the previous edges or the edges between all the vertices. Now if you look at vertex E, there's a vertex, at vertex E, there's an edge from D to E. It's a directed edge. It goes from D to E, okay? Now you may ask, what is the weight of this edge? In order to look for the weight of the edge, you need to look at the graph, okay? If you look at the graph here, you can see the edge D to E has a weight of 2. So the weight here is 2. Now similarly, let's do it for the remaining ones. Now the next vertex is D. the previous node for D is, this is the pi table. Pi basically is used to represent previous. So previous node. So for D, the previous node is A. That means there should be a edge from A to D. Now what is the weight of this? The weight of this can be found by looking at this graph. As you can see, from A to D there's only one edge and the weight of the edge is 1. So the weight of this edge also should be 1. Now next we look at our vertex C. There should be a there should be an edge from A to C. A is the previous node of C. A to C, and the weight of this edge should be 2, as you can see from this graph. That is the reason why I drew the vertices in the same places, so it becomes easy to correlate. No, so this is 2. Nicer. Then our next vertex is B. If you see, B originates from A, or A is the previous node of B. You can say it in any way, but that's just the general meaning. So there must be a vertex from A, there should be an edge from A to B. So there's the edge from A to B. Now, what is the weight of this edge? If you go from A to B, the weight of this edge is 2. So we just write 2 over here. Nicer, nicely done. And now lastly, oh wait, no. If you look at A, the previous node for A is S, no? So there'll be this thing, what do you say, edge from S to A, from S to A. And what is the weight of this edge? The weight of this edge is given by 1. So we get 1 over here. Nicer. So well, I guess this is the entire graph, and since this is the start vertex, it has no previous node, which is why if you look at the column carefully, for the pi table, it's basically null, okay? Because there's no node before this, no. This is where we start from, start vertex. If you like, you can mention that. This is the start vertex. And this is our, final answer, resultant graph. This is our single source shortest path graph. Single source shortest path graph. And if you look at the distances, okay? Like for example, I want to go to D. So my distance will be S to A, 1. And A to D, 2, no? So 1, 2. So 1 plus 1, 2. And now if you look at the D table, the distance to go till D is also 2. So it matches, no? You can check for E also. For E, it should be 4, no? So this is a good way to cross check. So for going from S to E, the distance should be 4. So S to A is 1. A to D is 1. So 1 plus 1, 2. D to E is again 2. So 1, 1, 2, 4. Correct? So the distances also are matching. And also, if you like, you can show the paths for each and every, each and every vertex. Basically, if you want to go to A, then S to A. Then if you want to go to C, it is S to A to C. Then if you want to go to B, it is S to A to B. This is for A, this is for C, this is for B. As you can show for remaining also. Let's do that, I guess. So we showed for A, B and C. Let's show for D. So for D it would be from S to A and A to D. For D it would be from S to A and from A to D. Correct. Then for E it would be from S to A and from A to D and from D to E. And this is the start vertex, no? So uske pehle there is no vertex, so you don't need to write uska. But this is basically like the path if you want to traverse from the start vertex to any vertex. See, this is for S to A, S to B, S to C, S to D and S to E. And I guess with that you can end this numerical. Bye bye.